Hello, my name is John Gabriel and this is the New Calculus channel. So today what I'm going to do is talk to you about one of the differences between the New Calculus and the mainstream calculus. And the difference is primarily this, that in the New Calculus there is no derivative at the point of inflection. Well, I'll qualify that. There is a derivative in terms of an angle. There is always a derivative in terms of an angle. But in terms of the tangent ratio of that angle, there is no derivative at a point of inflection. And the New Calculus is consistent. So for example, in the flawed mainstream formulation, with respect to the cubic, at the origin, there is a point of inflection, and the derivative there, according to mainstream calculus, is 0. But according to mainstream calculus, there is no derivative here in this particular function, which is the one that you see in red. It's actually x minus 1 to the power of a third plus 1. This is what GeoGebra generates, but if you simplify this, it's just x minus 1 to the power of 1/3. In any case, in your bogus mainstream calculus, you say there is a tangent line there, but no derivative. Okay, actually there is a derivative in terms of the tangent line. Now, your mainstream calculus is inconsistent because you can have a tangent line and no derivative, and you can have a derivative at a point of inflection. So, for example, if you had the cubic here, the mainstream academics will say there is a tangent line and its slope is 0. Okay, so generally, how is a derivative generated? Okay, let's see how a derivative is generated. What we do is we take the slope of the tangent line at any particular point, and we plot our derivative as the x-coordinate of the same point and the slope of the tangent line. So as you can see there, the slope of the tangent line at any point is simply the derivative. Now over here, according to your bogus calculus, there is no derivative because you don't have the tangent of pi radians divided by 2 is not defined. Right? But let's do this. Let's see how you can actually, well, I didn't mean to do that. Let's see how you can actually show that, oh, why isn't this coming on? Well, this is strange now. Okay, there you go. So now, in terms, what I'm doing here in the blues, I'm drawing the slope defined as an angle, okay? So if I do the slope defined as an angle, it's always defined, even at this point where in your mainstream calculus you don't have a particular derivative. So you can find the slope or the derivative function. This is the derivative function in terms of angles. So, and it looks something like that. You can see the green dotted line. That's what you'll obtain if you plot the derivative using the y-axis as the angle measure and not the tangent of the angle, okay? And always this derivative will have a minimum and a maximum. The minimum will always be at minus pi over 2 and the maximum at pi over 2, regardless of which function you are dealing with, okay? So now let's, for example, consider this function. Let's consider x cubed, like so. Oh, I think I need to put in a bracket. All right, let's do this. X cubed, bracket. Okay, so now, as you can see, let's just put the trace off for a second. This here, the green here, is a derivative function, and you can see it bears a little similarity to the actual derivative, which is a red function. When I say actual, I mean actual in terms of Newton's ratios, okay? In other words, a tangent ratio. But as you can see here, the minimum that this derivative can have is a 0 angle or 90 degrees, because this line here is asymptotic to pi over 2. So if I say y is equal to pi divided by 2, see that? So this function, the derivative function, which is the green function, is the angle derivative, and the red function is the tangent of the angle function, which, by the way, it doesn't really make sense to talk about a very high derivative value, because what's the maximum derivative this red function can have? Well, it's, in terms of angles, it's pi over 2, right? And so if we do the trace, we'll see, well, now I've kind of got to shrink this a bit so I can get my point. If we do the trace, we'll see that it's exactly the same as the angle derivative, okay? And what I've done here is I've just simply made this point here, this blue point here, the angle instead of the tangent of the angle. And every function is defined everywhere using the angle derivative. So for example, if you had to say, let's do this now, I just want to move this close here. Let's do this. Let's say that you have the sine of x, like so. And as you can see here, let's take the trace off, the green line there is approximately the derivative, okay? So if we turn the trace on again, we'll see again that is the derivative in terms of angles, okay? And it's defined everywhere. Now, of course, if you do something like this in your mainstream calculus, you don't really have a derivative, because this here is not in its irreducible form. For example, this sine 0 over 0 is defined in the irreducible form, okay? So obviously you wouldn't put x is equal to 0 in this particular representation, because something divided by 0 is nonsense. But if you reduce this, you'll see that it's a function which is very well defined at x is equal to 0 at this point here, right? Okay, and so it doesn't really matter what function you put in here. The derivative function will always lie between pi over 2 and minus pi over 2. All right, so let's take a look at this now, and just take the trace off so we can see what's going on. And so, for example, the quadratic function has this trace, right? Again, it's like an S shape, and it lies between pi over 2 and minus pi over 2. So in the new calculus, a derivative is not allowed at any point of inflection if the derivative function is formulated in terms of the tangent of the angle, okay? So otherwise, in the new calculus, there is always a derivative in terms of an angle. But the new calculus is consistent. It will not allow a derivative at any point of inflection, which is not the same as your bogus mainstream calculus, which says that x cubed has a derivative at the point of inflection here, but the other function that I mentioned right at the start of the video doesn't have a tangent line, doesn't have a derivative at x is equal to 1, because the derivative there is not defined in terms of the ratio, the tangent of pi over 2. Okay, so I hope that you've learned a lot from this, and also that it's occurred to you that Newton's formulation of calculus was not really correct, and Newton was really experimenting. Okay, so he didn't really understand calculus as well as I did, and neither did anybody else. And of course, if you study my new calculus, so if you go to my ebook, you will see here how I define the derivative and why there cannot be a derivative at a point of inflection. Because if you have a point of inflection here at this green spot, there is no m and n except 0. But in the new calculus, m and n cannot be 0, okay, because there is no parallel secant line with m equal to 0 and n is equal to 0. However, if you must know, it's very easy to detect an inflection point in the new calculus. it will be a point that will only satisfy this formula if m and n is 0 and there is no other m n pair. In other words, there is no derivative at a point of inflection. And so this is my free ebook, which you can download from the web. And I suggest you do that and read it, because it is the most important book ever written in mathematics. And there is a lot more than just the formulation of the new calculus. So if you're not already a subscriber, please subscribe to my channel and spread the news of this new calculus and my mathematics. There is a lot I haven't shared with the public because I haven't yet been recognized. So I hope you've enjoyed this presentation and that you will join me soon again for another interesting video. My name is John Gabriel, and this is a New Calculus channel. Till